Okay, lesson 5, exploring congruent triangles. So you should have seen similar triangles in grade 9. Similar triangles were when two triangles had the same shape but different sizes. And you did questions like, let's see if I can get some paper here. You would have seen questions like this. So these two triangles, there's kind of a triangle A, B, C, and there's a triangle A, E, F, we'll call it. So these are two different triangles, and they're similar to each other. We proved similarity by proving two of the angles were the same. In this case, they both share a 90-degree angle there and here, and they also both share angle A. They both have exactly angle A in them. So these two triangles, and we wrote it like this, ABC, triangle ABC, is similar to triangle AEF. So these two things are very similar to each other. And then you could solve questions based on that. So if you said this was, say, we'll do a really easy example. This was 15 and this is 5. So basically, you know from this fact that the big triangle is 3 times bigger than the small triangle, right? So the distance from F to A, we'll say, is 7. And we want to know what is the length of CA, is what we're trying to solve in this one. So this was also in the proportions unit. So you would have to set things up like a proportion. So you would say something like 15 over 5. The ratio of 15 to 5 needs to be the exact same as the ratio from C to A, all over the number 7. So this is our big triangle, this is our little triangle. And you'd set it up like that, and then you could solve by multiplying 15 times 7. But hopefully you can probably see this number over here is just 3, so it's 7 times 3. So C to A should be 3 times bigger than 7, which is 21, centimeters. So we have similar triangles. Similar triangles means two angles in each triangle is the exact same amount. Angle C is equal to angle F, and angle A is equal to angle A. Therefore, triangle ABC is similar to AEF. So now we're going to be looking at something pretty similar. It's just stricter, even stricter than that. So there's actually more math involved in this than there is in the unit that we're about to do. But we care more about the logic of it. We need to understand the rules, and we need to understand the arguments and the proofs and stuff. Like, can I prove it's a congruent triangle? And can I write the language correctly? So even though the math isn't as bad, there's still a fair bit of work to do. Okay, so the first thing I want you to do is take 10 or 15 minutes, take however long it takes, and try and finish this page on your own. It will take some thinking. You can work with your partner, Austin and Riley, and actually try to sit down. If you want some manipulatives, you can go grab some manipulatives, but actually try and build these triangles. So basically, if you're given this triangle at the top, I'll just walk you through the basics of what we're talking about. If you're given all the following information about this triangle, what do you actually need to know about another triangle to know it's the exact same triangle? Or on the opposite side of what information could you have and yet still have a different triangle? So what is necessary to know it's the exact same triangle, or what is not sufficient yet to prove that it is that? So anyway, take 10-15 minutes, pause this video right now, and try and fill in this page on your own. Okay, hopefully you've had a chance to look at a bunch of these questions. Now I'm going to try and walk through them. So if you want to duplicate this triangle, would you have to provide all the measurements? Would you need to know every single thing in order to know it's the exact same triangle? The answer to this is no. No, you don't need to know all. There are 6 measurements in here, so we're starting with the magic number 6. You don't need to know all 6 measurements, all 3 angles, and all 3 lengths. For starters, 1 is very easy to prove. You could be missing any single angle. If that guy was missing right there, you could obviously find him. If you knew this was 75 and this was 65, you would have to already know what that last angle was. It would already be given to you, basically. So you definitely don't need all 6 pieces of information. At most, you would need 5, but it actually is even less than that. So which 3 pieces of information could be provided for duplication to ensure that the triangle is identical? I actually kind of want to come back to this question. We'll come back to this one later. I actually prefer this one. Which combinations of given side and angle measurements do not ensure? I actually prefer to start the question with this. Do not ensure that only one size and shaped. So we're talking about, I probably should mention that at the beginning. This time we're talking about congruent. So congruent means it has to have the exact same size and the exact same shape. So size is determined by the lengths and shape is determined by the angles. All of it has to be exactly the same. So you need all 6 measurements to be the same. What information could you be given and not still know it's the same? The one I like is this one. And we basically have short forms for all these. This one is called AAA, which means angle, angle, angle. If you had all 3 angles, you would not have actually proven it's the exact same triangle. And this comes from our similar triangles that we talked about before, right? In these triangles, we know that these angles are the same, we know that these angles are the same, and that actually proves, because of the 180 rule, because they have to add up to 180, angle E has to be the exact same as angle B. So these 2 triangles, all the angles are actually the same on them, yet they are not the same triangle. These are not congruent, these are just similar. So if you have 3 angles, it shows it has the same shape, but does not necessarily have the same size. It could be a bigger version or a smaller version. It could be zoomed in or zoomed out. So AAA doesn't work. Similarly, actually, triple S does work. Yeah, triple S will work. Any 2 pieces of information will not work. So obviously, angle, angle will not work. Side, side will not work. Any one side and any one angle will not work. You cannot have any 2 pieces of information. That's just going to fail. And then what about the other ones? Let me go back here and look. So that 3, those 2, those 2, those 2. There's actually one more kind of important one that I'd want to draw out to, and that is if you have angle, angle, side, side, angle, side. Side, side, angle, it's called. So if you have angle, side, side. If you have these 3 pieces of information, there is not just one triangle you could draw. So basically, you know that there's going to be some dotted line here, but you don't know what angle this is. And this one could kind of come back and forth. It's kind of hard to show, but there is no one way you can do it here. So what 3 information, let's jump back to this one now. So what 3 things can actually prove it? 3 sides is actually good to prove it. So if you had all 3 sides the exact same, 1.95, 2.92, and 2.74, and hopefully this is probably one of the first ones that you discovered. If you had them, this must be the exact same triangle as this. There is no other way you could put in angles. There is no other way it could form an actual triangle unless they had the exact same angles. So that actually works. And then there's 2 more versions. Basically, all of the ones that we're looking for involve 3 pieces of information. Those are all the important ones. If you have more than that, it's very much likely it's going to be the same. And less than that, it's probably not going to work. So there is a couple other ones. I don't know if you discovered them or not, but the other 2 are SAS and AAS. So it has to go in order as well. So this is like side, and angle. If you knew this was 75, if you knew this was 1.95, and you knew this was 2.74, there is only one more triangle. There is only one triangle you could draw. It would have to connect these 2 ends together, and it would have to end up being the exact same triangle as the one you were looking for. So that's actually good. And this is the trickiest one. That means you know an angle. You know this angle is, say, 75, and you know this angle is 65. Angle, side. Yeah, so it cannot be this length in here. If you have this length in here, that would be ASA, and that's actually not good. You might not be able to prove it from that one. But if you have this one over here, then it is good. I think it counts for either side. It just can't be the one between them. So if you knew this was 2.92, that would actually be good as well. So there's kind of 3 successful versions of this. And we'll see that on the next page. Which combinations of given sides and angle measurements ensure that all the triangles are congruent? No, that's kind of what we just talked about. Okay, let's look at the rules. And we're going to actually kind of talk about this with like proofs. So there are minimum sets of angles and side measurements that, if known, allow you to conclude that 2 angles are congruent. If 3 pairs of corresponding sides are equal, then the triangles are congruent. That is known as side, 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 or SSS. So this is our first rule. It's called SSS rule. So if I'm asking you, prove these triangles are congruent, you wouldn't be able to just say SSS, therefore congruent. That's not good enough. We need to see a bit better than that. The vertexes, or the vertices, are always capitals. Hopefully you remember that means their opposite sides are lowercase. This is little b, this is little a, this is little c, this is little y, this is little z, this is little x. So you would actually have to list, and I'd want to see it exactly like this. You'd say b is equal to y, a is equal to x, c is equal to z. So therefore, triangle ABC is now congruent. It pretty much is always written this way. It says equal to with a squiggly line. That means congruent to. It's equal to in shape is the way that I interpret that. Triangle XYZ. So these are all capitals now. We're talking about them in terms of their vertexes. If you haven't seen this symbol before, it kind of mentions it on the other page. This means so therefore. Triangle ABC is congruent to, equal to in shape with triangle XYZ. So that's congruency. Because, we could say because USE, if I can spell, SSS, because of rule SSS. So we've got our 3 side lengths. Because of rule SSS, these things are congruent with each other. So the language is really important. I probably haven't mentioned this yet, but in the 20-2 curriculum, we have a bunch of units on reasoning and proofs. So there's a lot in this course about actually arguing. You need to be able to argue mathematically. You need to be able to convince the reader. Not just convince the reader, you need to prove it, is what you're doing it. So I've actually proved this. I proved 3 side lengths are equal, and I've said because of the rule of SSS, these 2 things are congruent. This is going to be a big focus this year, so we really need to develop these skills. Okay, let's try number 2. Number 2 is SAS. If 2 pairs of corresponding sides and the contained, this is really important, the contained angles. Contained means that it has to be the angles between the sides. So our sides are here and here. It can't be this angle or this angle. Has to be that one. That's why it's in order. S side, angle side. The order actually matters. So this is SAS, not SSA or ASS. So let's prove that one. We would say length C is equal to length Z. If you put the lowercase, that stands for the length. You don't have to, if it's not the capital. Alternatively, you could say the length of B to A, like that, but that's obviously more work. If you've got all the vertices, just use the lowercase. That stands for the length. I'm good with that. Also, little a is equal to little x. Also, angle B is equal to angle Y. How do we know it's equal? It's telling us. We're not guessing. This line, a single line and single line means these are equal. A single curve and a single curve means the angles are equal. Double and double, they're equal with their counterparts. So the shape itself is telling you. We're not making guesses. These ones look equal. And in fact, we're going to prove they are equal because we're going to say they're congruent triangles. But you can't actually conclude that until you reach the other conclusion. So therefore, because of SAS, triangle ABC is equal to congruent with triangle XYZ. Lot to write. Take it seriously. Like I said, I was marking these in the summertime, and I saw people just like write like a check mark or a yes or the congruent symbol or something. And these were like 2-mark questions, and they got 0.5 out of 2. So they end up failing the assignment just because they didn't think they needed to bother actually doing more detail. You do. I need to see all of this. Basically, this is 1 mark for identifying what's true. The other mark is arguing the conclusion based off it. And not just the statement, and also the argument why. So you need all of that. Okay, the last one. If 2 pairs of corresponding angles and the contained sides. So this time it's the contained sides. It's the side between the angles. If all that's true, they are congruent. It's ASA. So in this one, this should be doubled up. Doesn't really show it. Because these are single lines, really one of them should be double. This should be a double and this should be a double, I would assume. So in this one, angle B is equal to angle Y. Length A, little a, is equal to little x. And angle C is equal to angle Z. No funny symbols here. We're not doing congruent or anything. This is just equal. Whatever this number is for the angle is the exact same as the number there. They're completely equal. But then we get to the other symbol. So therefore, because of ASA, triangle ABC is congruent with triangle XYZ. Okay, that's pretty much it for this unit. Basically, these are our only 3 rules. This is the minimum amount of information you need to be able to prove a triangle. Sometimes you can do it some other ways. Like this one is a very common exception. I might give you, say, this angle and this length over here, and you say, oh, well, this isn't a contained length, I can't actually prove it. But what you can do is, if you know 2 of the angles, you can solve for the 3rd angle, right? So you could actually solve for the angle on the other side of it, and then as long as you've proven those ones the same, then you've actually proven it. So really it's any 2 angles and any side. So really AAS will very quickly be true. if you can actually extend it, if it actually becomes true for the other side. So you should be able to change that one across. So that's the one note I had there. The other note, congruency. Let's just make sure we understand what congruency means. So similar was the same shape, triangles. That means all the angles were the same. It's the exact same shape from one to the other, but the size could be different. So our proportions kicked in for that. Congruent is the really strong one. Congruent means it's the same shape, so they are similar triangles, but it's also the same size. So all the lengths are the exact same numbers as well. The only thing that isn't true for congruent is the orientation. So one of these triangles could be spun around. So they don't have to be facing the same way. That's the only special thing about congruency. So they can be facing other ways, but they have to have the same overall shape and overall size if you actually match them up. So it won't always, like these two angles, if they're the same, they might not always be in the same corner. Y could have been like up here or something. We could spun this triangle around and it still would have been true. So you got to watch for that. But yeah, similar versus congruent. And on their last page, the symbol, 3 dots, represents therefore. I usually say so, therefore, 3 dots, so therefore 3, whatever you call it. In geometry, this symbol generally is used when stating a conclusion drawn from preceding facts or deductions. So this is kind of our big thing here. It's all about the argument. So we use this symbol when we're reaching a conclusion based on facts we've already established. And that's exactly what we were doing here, right? We said, here are the facts, and because of these facts, so therefore I can do this because of this argument. So it's all kind of drawn together. Okay, that's it for this unit. Try the assignment questions, and let me know if you're having any difficulties.